Assalamu alaikum. How are you, my dear students? Hope you'll be fine and okay. I welcome you all into my today lecture. In our today lecture, we will study the back EMF and the transformer. So let us start with the name of Allah Almighty. And the first topic is the back EMF. The back EMF. Usually, we will study the back EMF, particularly in motors, right? There is back EMF in generators also. Now, what is this back EMF? Or sometimes we call it the counter, we call it the, we call it the counter EMF. The counter EMF which opposes the back EMF is the counter EMF which opposes the change in current, the change in current, the change in current which produces it, which produces it, which produces it. This is what a very simple, in a very simple way, I will tell you that in fact the back EMF is, this is the generator effect in motor. I will call it what? I will call it the generator effect, the generator effect in motor, effect in motor. Why? Because we know one basic principle that whenever there is changing magnetic flux in the nearby region of a coil, then there will be induced EMF in the coil. So if you see, look at this diagram to introduce or to explain the concept of this back EMF in motor. Let us see that here we have the motor, right? Now you know that the motor is supplied with some alternating current. Now you know that as the coil is rotated inside the magnetic field, then there is a changing magnetic flux. And that changing magnetic flux in turn produces its own induced EMF within the coil. So that causes the induced EMF within the coil itself. For example, look, that is, if I just let me give you the inner view of it. Let us suppose, for example, that if we have this as the North Pole and this is the South Pole, right? And if we have this as the look, this is the motor, okay? Now you see that look, there is the inside it, there is a coil, as you see. Look, now this coil is supplied with some source current, and that source current I represent by I. Okay, now this causes the coil to rotate inside the magnetic field, and this is due to the effect on force on current carrying conductor inside the magnetic field. And let us suppose right now, without applying the Fleming left hand rule, because you already know, but I just guess that let the couple or the torque produced by this coil is this one, right? That it is what? That it is in this direction, right? And let we call that it causes a clockwise torque, right? This clockwise torque tend to keep the coil rotating. as long as the current is there. Now you know that this coil, it also rotate inside the magnetic field, and there is changing magnetic flux. So beside the source current I, beside this source current I, there is another current, induced current, in the direction opposite to this source current, and I would label this like this one, in this direction supposed to be. Oh my god, sorry. That this opposing current, let's say it will be in this direction, the opposing current. This is the induced current, the current induced. Now this induced current tends to rotate the coil in direction opposite to uh, in the direction opposite to the one caused by the source current. So this induced EMF tends to create a torque in this direction, as you see. Look, so you know that this causes a counterclockwise torque. Now the two opposes each other, and this back EMF tends to slow down, the motor, to slow down the motor. And this is also in consistence of the law of conservation of energy. In order to keep the motor rotating, you need a constant supply of voltage or potential difference provided. Now let us see that all the game is the game of the energy. Now look, for example, if the potential drop here is V, if your supplied potential difference is V, in order to calculating the back EMF, calculating the back EMF and its effect. Now you see, look here, that the total potential difference which you provide, the source potential difference, is V. This source potential difference consume at two places. One, there is what, look, if I label that this is the load resistance, or it is load, motor is our load. One, that it consumes, that is the potential difference across the load resistance, right? This is our input. Okay, this is what, this is input, and input equals output, the output. And in the output we have one this, and one we have the induced EMF, right? So how much current the load drop from the circuit can be then easily calculated by using this equation, V minus, like this. Clear? Or what we can write like this is that this current equals the terminal potential difference across the load resistance, the source potential difference into the induced EMF divided by the resistance. So this is actually what, this is actually the back EMF. This portion, this is what, this is the back EMF caused due to the generator effect in motor. And this is what, this is the IR drop, yeah, the terminal potential depth. This is the the source potential, difference, the source potential. And this is what, this is the potential drop across the load, potential drop across the load, across what, across the load. Now once in the normal conditions, right, when there is no load applied to the motor, right, and when you are simply running the motor, then if you look into this equation here, if you look into this equation here, what happens that look normally as the motor gains speeds, then what happens, this induced EMF increases, right? And the induced EMF increases as the motor gains speed, and the current what, and the current decreases. Now that is that once the motor attain a constant speed, then the induced EMF, this E, will remain at a certain maximum value once the motor attain a constant speed, and this is at its maximum value at that point. And what happens, resulting what, resulting decrease in I, resulting decrease in current. Now that current is at its limiting value. This current is enough to keep the coil moving, right? And it does not produce excessive heat energy or power dissipation. And this is one of the reasons that the motor is continuously working. Now once if you increase the load resistance, for what, for large load, what happens, for large load the motor slows down, right? For large motor the motor slows down. For large load the motor slows down, slows down. And once when the motor slows down, then what happens, that is, when it slows down, then this causes the induced EMF nearly to fall zero, right? And then your equation turns to what, that I becomes what, V0 like R. And there exists what, there exists a large I in the windings of the coil and causing power dissipation. And this power dissipation is P equal I square R, and the winding overheats, melt, and we say that the motor burns. So this is the back EMF and its effect, right? The back EMF can be maintained at a constant value, right? And this can be done by that is by limiting your load, right? Once if you increase the load, then they may cause or put you in trouble, right? Because they will reduce excessive heat. Our next topic is the transformer. The next is transformer. Now, what is transformer? Transformer is the device or instrument. It is the device which is used to increase or decrease the value of AC quantities. Or we can say to step up or step down the AC, and hence can be used for power transmission, for the power transmission. transmission in the powerhouse. Now, one thing which I want to tell you, and you need to understand this, that remember, beside all these, transformer is a machine, and remember, it cannot, you must remember these things in advance, it cannot increase or decrease the power. Remember, though power output will be less than power input, so we cannot use transformer to generate power. Remember, it is a machine, okay? It does not have any source of energy. It does not have any source of energy of its own, any source of its own, source of energy, right? Nor it can't store energy as well. It can't store energy. You need to remember this. The working principle of the transformer, the working principle, the working principle of the transformer is based on the phenomena of mutual induction. Now, in order to explain the working of the transformer, let me first talk about its structure. A simple kind of transformer consists of iron, it consists of the iron core, but I will come to the iron core later on. That it consists of the primary coil or winding, the primary coil. This primary coil has NP number of turns, the number of turns in the primary coil. Here input is supplied on the terminal of the primary coil. Input is supplied here, and that input, rather it is an input terminal, and we label the input terminal as VP. So that is, and remember, only transformer works with AC quantities only. Remember, AC quantities only. It cannot work with a DC because DC cannot have changing magnetic flux. And second, we have the secondary coil. The secondary coil, which you see in the diagram here, the secondary coil. This secondary coil has number of turns, we label as NS, the number of turns in the secondary. Here, the number of turns in the secondary, NS. Number of turns in the secondary, NS. Number of turns in the primary, NP. Here we supply the output voltage. The output voltage is this AC, and it is labeled as VP. And here we will gain again the output. This is our output. The output here is the VS, right? And here is our input. Okay, and then we have the second coil. Now the soft iron core. Soft iron core. Both the coils are mounted on the soft iron core. Both the coils are what? They are mounted on the soft iron core, and this soft iron core is used for linking magnetic flux. Linking magnetic flux, for the linking for the linking magnetic flux from secondary to from the secondary to the from the primary coil to the secondary coil, as you see here. Now let us see for the voltage induced across the secondary. From the Faraday law, to explain the working, let us start from the Faraday law. Faraday's law. The Faraday law says that the voltage in the secondary is equal to the number of turns in the secondary and to the rate of change of flux in the secondary coil. The negative sign indicates the direction of the induced EMF, and I already told you NS is the number of turns in the secondary coil. Now the same is this same magnetic flux actually pass from both through the secondary and the primary. Then the magnetic flux through the primary coil will be in the same manner as like this, right? When the transformer is ideal, right? Now look, we have got these two equations. Now when we divide equation 1 by 2, then we get one of an important relationship, Vp into Ns by Np, and this implies that the Vs equals Ns by Np into Vp, where you know that Vp is the potential difference across the primary terminal. Now look, as you see here, there are cases. If Ns is greater than Np, then what does this implies? This implies that the ratio of Ns by Np will be greater than will be greater than 1, and this will cause Vs to be greater than Vp, right? And this will make your transformer step up, right? The output voltage will increase than the input voltage. Now don't confuse this thing that that there is the violation of the law of conservation of energy. It is potential difference, it is not energy or power, and you will see it right now. I will explain it to you. Now for the case B, if N is less than Np, what happens? The ratio of Ns by Np would be less than 1, and you are causing Vs smaller than Vp, and the transformer will be a step down transformer, step down. It will be a step down transformer. It will be what? A step down transformer. Now let us see here that for look, so you have seen that it all depends the turns ratio. We call this as the turn ratio. The Ns Np, that is called the turn ratio. If the turn ratio is greater than 1, causing the transformer to be step up. The turn ratio is less than 1, causes the transformer to be step down. Now, I just want to explain to you that it is at the cost of something else. right? So I just want to discuss the power in the transformer, right? And then you will easily understand this. Now, as we know that the power out for an ideal transformer, power out must be equal the power n, right? If the transformer is ideal. Now you see that, look, what is power? Power is like I into V, I into V, product of current and potential difference. Since this is at the secondary terminal, ISVS and IP VP. So if you increase the secondary voltage, the secondary current decreases automatically, so that you have to have this factor remain the same. This factor will remain, this factor will remain the same. This will remain the same. And if the transformer is stepped down, if this decreases, if Vs decreases, the Is increases, and you have the same thing again. So there is no power loss, there is no violation of the law of conservation of energy. And let us see it. For example, why I'm saying this thing. The Vs by the Vp from this equation, I can write by Ip into what? Into Is. So this indicates that Vs is inversely proportional to Is, right? That the number, remember, don't confuses this with the Ohm law that V is directly proportional to I. That is entirely a different thing. Here the situation is very much different, totally different, 180-degree different. Don't confuse it with that. So the Vs is inversely proportional to Is. So if the Vs increases, the Is automatically decreases. It is not in your hand. Now let me tell you why. Because if I just label this as one equation, and if I just do that equation where this equation, let us see this equation. Okay, if we equate these two equations, then what happens? Then the IP by Is equals here the Ns by Np, right? Yeah, the Ns by Np equals Ip by Is. Now you know that you have very two or important, the all important equation I want right here. Now look, your first equation, the Vs, this is which one? The first equation here is the Vs by Vp equal Ns by Np. You have won this equation. Now, in order to increase Vs, you must increase Ns. But if you increase Ns, Is automatically decreases. Why? If the number of turns per unit length increases, resistance increases and current might decrease, right? So the Is decreases. So if the Is decreases, then what happens? Because you know Is into Vs, Ip into Vp. So it gives you the same thing again. Look, if you want to increase Vs, you will increase Ns. But if Ns increases, Is automatically decreases. Why? Because Is Ip Np by Ns. So you see here that Is is inversely proportional to Ns. So increase in Ns in decreases Is, right? So you have the same thing again. So this tells you that in the transformer, law of conservation of energy is even not violated, right? Now let us discuss the power losses in the transformer, that how the power losses in the transformer can occur, right? The power loss in transformer. Power loss in transformers. Yeah, energy loss in transformers. The energy loss in the transformer can be, first of all, I will just write the winding of the resistance of the coils of the coil itself, because you know the coil is good conductor of electricity, right? So when the current flows through the coil, then the coil has resistance, and there will be a power dissipation, I square R of the coil, resistance in the coil. So one of the power loss is here. Now how to minimize this power loss? In order to minimize this power loss, we can reduce the resistance of the coil by using thicker wire, right? And wire of very low resistivity and of thicker wire. Okay, so this will help us reduce the reduce the power dissipation, right? So that is the energy, right, which is dissipated in the form of heat due to the coil own internal resistance. And the second one is the flux leakage. Flux flux leakage. What? The flux leakage. Some of the flux you see here, that some of the flux may miss, right, may miss the, some of the line may miss passing through the secondary coil. So we say that that is the loss of the flux. So the loss of the flux can cause what? The loss of the flux can cause the wastage of our input energy. That means that all of the flux in the due to the primary coil not passes through the secondary file due to its fault in design, you may say. So this is one of the reason that the secondary coil may be all around, or the secondary coil, to reduce the flux leakage, the secondary winding or coil is usually placed on the primary coil by insulating them from each other or from any direct contact, but they are wound over one another. So this may reduce the flux leakage, and maximum flux can pass through the secondary coil. So winding over one above the other may reduce this effect. The third one is the AD current. Due to what? Due to the AD current. The AD current, as I told you, that AD current is the intended or the unintended current reduced. So look, AD current is produced in the windings of what? No, sorry, in the soft iron core, right? The core material, as you know, this is the iron core, the iron core. So now due to, because of that changing magnetic flux, there is a current that produces inside the iron core. Now as you see, this is the AD current, it is indicated here, right? That is perpendicular to the direction of the changing magnetic flux. So this AD current produces again power loss, I square R, right? This is which current? The current due to the AD current effect, and R is what? The resistance of the soft iron core, yeah, of the iron core. So some of the energy is lost here in the form of heat, and very large amount of heat can be dissipated. So to reduce this effect, instead of what? That, look here, you see that the iron core has a thick, what? Here, thick iron core. The iron core is thick, so definitely the resistance will be smaller, less resistance, and more current will be flowing. The more AD current will be flowing. So to avoid this, we use the laminated magnetic core are iron sheets, right? And there are numerous iron sheets together, right? Like this, as I'm doing, for example. Let me just take the, so here, let me do this for you. For example, if you have what, that to cause this effect, to reduce this effect, here you see, look, one iron sheet like this, it is again too big. The iron sheet, like for example, we will make the iron sheet by using this. Okay, see here, you have one iron sheet, this, okay, another iron sheet is then placed above it. Let me choose a different color so that we can differentiate. Okay, then like this, iron sheet above it, and then another iron sheet like this. All the iron sheets are then combined, they are laminated. Laminated means they are painted, okay, so that they insulated, they are insulated, there is insulation. That insulation, insulated, that reduce the general thickness, and current cannot pass from one sheet into another, and therefore it cannot generate excessive heat in the iron core. So in this way, AD current effect can be minimized. And the fourth one is the fourth, the hysteresis. Now, what is this effect? It is the amount of energy. It is the amount of energy lost or consumed in the magnetization, in the magnetization or demagnetization, or demagnetization of the iron core, of the iron core over one complete cycle of AC, one complete cycle of AC. Okay, so you know that, look, there is a soft iron core. This soft iron core is magnetized and demagnetized again and again over one complete cycle of the AC. So as long as the AC input is supplied, there is a continuous magnetization and demagnetization of the core of the transformer. So for this purpose, to reduce this effect, because it depends on the nature of the substance, depends on the nature, usually the nature of the substance, right? For example, we have two kinds of substances: hard ferromagnetic substances, ferro, and soft ferromagnetic substances, magnetic substances. For example, if you use a steel iron core, then steel is hard ferromagnetic substances. It requires a lot of energy in magnetization and demagnetization. So for the transformer, that is not a suitable option. Why? Because we don't need any magnetic effect from the transformer, right? So a lot of input energy will be wasted. So to minimize the hysteresis, we need to use the soft ferromagnetic substances like iron. So iron is best in this case, because iron requires less energy in magnetization and less energy in demagnetization as compared to the hard ferromagnetic substances. And this is just one of the effect which I explained, and inshallah we will study this as a topic in the next chapter. So this is all for today. So thank you very much for being here. So see you in the next lecture, inshallah.